Hello, you're welcome back. All right, so we'll continue from where we stopped. Now we are going to be looking at convection. Okay, now it's another type of heat transfer. Convection is actually a type of heat transfer in which heat is transferred from one part of a fluid. Okay, it's basically a heat transfer that happens in a fluid, that takes place in a fluid. And of course, you know that fluid is can either be a liquid or a gas. That's a fluid. Okay, so now the heat transfer that actually takes place in liquid or gas is regarded as convection. Okay, now that such heat transfer is a type of heat transfer that takes place in a fluid by the actual movement of the molecules of this fluid from one part of the medium to another. Okay, now to illustrate this, now let's look at what happens when you heat water. Now this is actually water that is actually being heated. You discover that at the point where at the down part of the container, okay, the temperature of the water molecule actually increases, which causes bubble, the water to actually create a bubble, right? And that bubble, due to its volume and lightness, okay, buoyancy, will actually rise. So as you heat the liquid, the molecules at the lower part of the liquid actually uh, the blow bubbles goes up and give way for the colder liquid to actually comes down to replace it. Okay, hot molecules goes up while cold molecules comes down to replace the hot molecules, and that is actually how the convection. Okay, we call it a conventional current. Keep on, okay, works. That's how it works. That's how it would. That is the cycle that will keep on. That will keep on operating until the entire liquid is actually heated, and of course all the molecules of the liquid, okay, gets to a steady temperature. All right, so such is what is known as convection. So it takes place in liquid and of course in gas. Okay, so now convection can actually be of two types. We have um, convection that actually happen naturally, natural convection, or the convection is actually forced convection. You have a forced convection. So what is different between the two? Now, if the convection is natural, of course, natural convection actually happens when the hot fluid, are you okay, rises uh, naturally without being forced to give way for the cold one to replace it. Okay, so they actually rises by themselves due to their buoyancy, because once the fluid or the molecules actually uh, gains heat, it will expand. As they expand, just like the same way balloon expand, and it will actually float. That's what happened. It will actually rise, okay, naturally, to give way for the hot molecules to come and replace it naturally. But in a forced convection, it doesn't happen naturally. It is actually being forced by an external agent. Okay, for example, when you actually use fan, okay, to blow air around that particular region, you are going to create a force convection, because the fan now will force, okay, fan actually forces molecules to move. Okay, now as the molecules actually moves, then of course such a convection is being set up. All right, so that is actually a force convection. So if there's no external factor, then definitely such convection is actually natural convection. So please take note of that. And of course, an application apart from this boiling of water, there's uh, an instrument known as chimney. Okay, chimney is one way of actually uh, cooling a house. Okay, a chimney is actually if a chimney is actually being constructed in a building, okay, it simply means that the roof of that building as one part is actually opened. Then what actually happens? Okay, the roof of the building, let's say at two end is opened. One is where hot air actually rises up, while the other walls, the opening is where the cold air actually comes in. So now in such a building, um, heater is actually being created, any form of heater, okay, to heat the air around that particular room. So as the heat is actually supplied to the air around this region, then what happens? Such the air expands. As they expand, okay, naturally they actually moves up through the chimney outside the room. So as the hot air actually move out, then what happened? So this is the hot air molecule. Then what happened? Okay, as hot air goes out, cold air actually replaces it. So by such natural convection, you are able to cool this particular room, okay, by creating such convection. And of course, another example is known as land sea breeze. So let me not go into details, okay. So that is how actually convection work. So please take note of that. Now we are going to discuss radiation. Okay, now this type of heat transfer is a type of heat transfer, okay, that does not require any material medium, no material medium for this heat transfer. So we are not looking at either solid or liquid, okay, solid, liquid, or even gas, as we have already discussed. So in radiation, there is no agent, there is no material medium that are involved in this heat transfer. There's no solid, no liquid, and of course, no gas. None of them is involved. Okay, so rather the heat is actually being transferred through a vacuum. A vacuum is actually a medium that doesn't have any of this state of matter. Okay, so for example, the heat that is actually comes from the sun, okay, actually reaches the earth through radiation. So please take note of that. So it is not liquid, solid, or even gas that transfer the heat from the sun to the earth. It actually transfers to the earth through a process known as radiation. Okay, so now I'm going to discuss what is known as black body radiation. Black body radiation. Now, what is a black body? Now, by definition, a black body, okay, is actually a very good, I will call it a perfect absorber or emitter of radiation. Okay, a black body is a perfect absorber or emitter of radiation. So which simply means that if the black body, okay, is used to absorb the radiation, it absorbs it very well, perfectly. If the black body is used to emit the radiation, it emits it perfectly well. Okay, so that is why it is not advisable to wear black clothes on a hot sun, because black clothes have the ability to absorb substantial amount of heat during hot sun. Okay, so please take note of that. So now for us to study black body radiation, okay, we actually set up an experiment in which, okay, a container, which of course is the inside is actually painted black, or is coated black. Okay, it's coated with probably a black color, whatever. Then radiation is meant to enter into this particular container. Okay, so the radiation enters, of course, it will undergo multiple reflection. Now this radiation now is actually being, that is being absorbed by this container, is being heated. The container is being heated. Okay, and the radiation that is absorbed by the black body container is studied for different temperature and of course uh, wavelength. Now it is discovered that as the temperature of the uh, of the black body actually increases, then the wavelength of the radiation that it can emit, okay, also reduces. So what does that simply mean? It simply means that the wavelength is inversely proportional to the temperature. So the more you increase the temperature, the lesser wavelength you're going to have. At a higher temperature, you have less wavelength. Okay, as less temperature, uh, you have a higher wavelength. Like of course, you know very well that if I should actually change this proportional sign to an equal to, I have to introduce a constant. Okay, so the constant, I'm going to introduce a constant. Okay, that's k all over t. So if I should actually cross multiply, the constant is going to be equal to the wavelength multiplied by the temperature. Okay, so this constant k is a constant known as Wien's constant, Wien's constant of black body, Wien's constant, and of course it's a constant value. Okay, it has a value. So such a Wien's constant has an approximate value of 2.88, 2.88, 2.898, please pardon me, 2.898, then times 10 raised to the power of minus 3. Okay, and of course it's given a meter Kelvin. All right, so now please take note of this. Now let's look at a typical example. A typical example is a question here. I have a question. A furnace is at a temperature of 300 Kelvin. So the temperature of the furnace is 3000 Kelvin. Please pardon me. A very high temperature, 3000 Kelvin. Okay. At what wavelength will you expect the greatest intensity of radiation? At what wavelength will you have? Okay, what is the wavelength will you be able to have? That's, we are looking at the maximum wavelength. Okay, what's the maximum wavelength that gives the greatest intensity? Okay, so please take note of that. So for you to actually get that, the maximum wavelength wavelength maximum is going to be equal to, from the formula, Wiens constant divided by the temperature. So that's going to be equal to 2.8 2.898 times 10 raised to the power of minus 3, then divided by the temperature, which of course is 3000 Kelvin. So I'm sure if you divide that, you will have the answer. Okay, let's divide that. So 2.898 divided by 3000. So I'm having approximately 9.66. 1, 2, 2, 3, 4. 9.66 times 10 raised to the power of minus 10 raised to the power of minus 4. Okay, then of course times 10 raised to the power of minus 3 already here. So the wavelength, the maximum wavelength is going to be equal to 9.66 times 10 raised to the power minus 4 minus 3 will give me minus 7. 10 raised to the power of minus 7. And of course that is measured in, wavelength is always measured in meter. So please take note of that. All right, so I'm going to proceed. I'm going to proceed with a law known as Stephan's law of radiation. Stephan's law of radiation. Stephan's law of radiation. So according to Stephan's law of radiation, he said that the rate at which a black body, okay, please pardon me, radiation. So according to the law said that the rate at which a black body radiates energy, the rate at which a black body radiates energy per unit area, okay, is directly proportional to the absolute temperature of the black body raised to the power of 4. So E here is the rate of energy a black body will radiate, okay, rate of energy per unit area. Of course, you already know that rate of energies, of course, is power. Because rate of energy is energy all over time. So the SI unit is going to be watt. Then area is meter square. So that means invariably now, E, the symbol E is having the unit watts per meter square. So of course, you know very well that if I should change this to an equal to, I'm going to introduce a constant. So this is the symbol of the constant, all right? And that constant is, this constant I've introduced is a constant known as Stephan's Boltzmann constant. Stephan's Boltzmann, okay? Of course, the person that actually stated the law. Boltzmann constant. Okay, so, and of course, every constant should have a constant value. So that constant is given as 5.7 times 10 raised to the power of minus eighth. And of course, you should know what the SI unit will be. Okay, the SI unit already, you know that the SI unit of this is watts. The SI unit of the E is watts per meter square, right? So if I divide by the temperature, temperature raised to the power of 4. So that means the SI unit is going to be equal to of the constant is watts per meter square. Then of course per Kelvin raised to the power of per Kelvin raised to the power of 4. So please take note of that. So anytime you are being asked to calculate the rate of energy per unit area, okay, by a black body, the rate of energy emitted by a black body per unit area, you multiply the Stephan's constant by the absolute temperature raised to the power of 4. All right. So now, what happens if this particular body, the temperature of this body actually changes from initial temperature to final temperature? Okay. Let's say we have a situation where the temperature of the body changes from T1 to T2 to T2 to T2. So how will I be able to get the energy that is emitted by that body? Of course, the rate of energy emitted by the body per unit area when the temperature changes is going to be equal to simply the Stephan's constant, then multiplied by the temperature change. Okay, so that's going to be equal to the final temperature raised to the power of 4 minus the initial temperature T1 still raised to the power of 4. Okay, so in the case of changing temperature, right? So I hope that is well understood. Okay, so we definitely got to apply that. I'm going to solve some question. Okay, now don't forget that let me start the formula again. Okay, now we use this basically. Okay, this formula is this when we are dealing with black body. Okay, black body radiation, then the formula is definitely is going to be the constant, of course, T2 raised to the power of 4 minus T1 raised to the power of 4. Okay, so we use this constant, just the Stephan's Boltzmann constant when it is for a black body. But what if what we are actually dealing with is not a black body? Okay, we have another body entirely that is not a black body. So if it is not a black body, then definitely there is going to be, I'm going to introduce another constant. Okay. So now if we are dealing with another body that is not a black body, then another constant actually comes in. Right? So I will end up having another constant, epsilon 0, before now multiplied by the Stephan's constant, okay, of course, times t raised to the power of 4, t2 raised to the power of 4 minus t1 raised to the power of 4. Please pardon me. T2 raised to the power of 4 minus t1 raised to the power of 4. Okay. So now the question is, this constant I've introduced now that is not is a multiple, a constant that is for a non-black body. What is it called? Okay, so this is a constant known as relative emittance of that particular body that is not a black body. Relative emittance. So we simply mean that that's another constant, okay, which I need to introduce to the Steph Stephan's equation if I am not dealing with a black body. Okay, so Please take note. And of course, in the question, we are being asked to evaluate the rate of um, emission, okay, of energy by a non-black body. You will definitely be given this constant. All these constants will be given in that particular question because you don't need to actually cram them. Okay. So now let's now flow with your question. Okay, I'm gonna start with the very first question. It goes this way: a spherical toxin has a diameter of 4.0 cm. Okay, so the diameter of the toxin, of course, the toxin is spherical, and we are told that the diameter is 4.0 cm. Of course, I need to convert that to meter. Okay, that will be 0.04 meter. Okay, so let me continue the question. And emissivity. Okay, so that emissivity here is same as the relative emitters. So the emissivity epsilon, all right, and is given as 0.35. Okay, so the question is find out the energy lost by the radiation in 1 second when the temperature of the ball when the temperature of the ball is equal to 29 2927 degrees Celsius. Okay, 2927 degrees Celsius. Now, don't forget that this temperature is given degrees Celsius, and the temperature I use here is absolute temperature. The capital that is as absolute temperature. So I'll have to convert this temperature to definitely I have to convert it to an absolute temperature. Okay. So of course, how do I convert this to an absolute temperature? By adding 273 to it. So to convert it to an absolute temperature, I have to add 273. So let's do that. I've got a calculator. 2927 plus 273. So that's 3200. So 3200 temperature in Kelvin. Okay, so that's absolute temperature. Then of course, for me to now get that the rate of emission of energy radiation, okay, you know the formula that is going to be equal to the relative uh, emitters or the emissivity, then multiply by the Boltzmann constant, okay, then times the area, because the area of the area of the tungsten, then of course then times the temperature raised to the power of 4. So let's put those value. So this is going to be equal to 0.35 multiplied by, okay, the relative emitters, the uh, Stephan Boltzmann constant, okay, which of course we already know that the constant is 5.7. I'll give you the constant times 10 raised to the power of minus 8, then multiply by the area. This is a sphere. Of course, you know how we actually evaluate the area of a sphere. Okay, the area of a sphere is 4 pi r square. That's going to be 4 pi, then multiply by r. R is actually the diameter divided by 2. So that means R is going to suppose is going to be 0.04 divided by 2. That is 0.02. Okay. So I'm having 4 times 4 pi times 0.02 square. 0.02 square. Then before I can now multiply by the, okay, before I now multiply by the temperature. So temperature raised to the power of 3200 raised to the power of 4. Okay, so let's actually evaluate that. 3200 raised to the power of 4. Let's start multiplying. 3200 raised to the power of 4. They are now multiplied by times bracket open 0.02 raised to the power of 2. Then times pi is 3.14. Then times 4 times 5.7. Then times 0.35 times 0.35. Okay, so I've not actually worked on this. Okay, so I'm having 10509. Okay, it's just a long digit, but okay, by multiplying by 10 power minus 8, I have to move the decimal point 8 times backward. 1, 2, 3, 4, 5, 6, 7, 8. So invariably now, if I should stop at this point, now I'm gonna have, okay, approximately 105. 105. 10509. 10509. Okay, but that's where I stop exactly. And of course, you know the SI unit. That's gonna be watt, of course, per meter per Kelvin. Okay, so that is by the way. So we are going to look at more questions in the next video. Okay, so see you in the next video. Thank you very much.